Okay, so let's look at some problems. Mars has a mass of 6.46 times 10 to the 23rd kilograms and a radius of 3.39 times 10 to the 6 meters. What is the acceleration due to gravity on Mars, and how much would a 65 kilogram person weigh on this planet? Now, in order to answer B, we have to answer A first. List out all your variables, and we know that the mass and the radius. Using that, we can use the equation of gravity, which is gravitational constant times mass over radius squared, will give us the acceleration due to gravity. When you plug in your values, you see that your gravity will be equal to 3.75 meters per second squared. Now, using that, you have to remember that weight is equal to mass times little g. And since you already have your little g, and they give you that the mass will be equal to 65 kilograms, then you can plug it in for the formula and see that you will weigh 243.71 newtons in Mars. Let's look at another problem. On Earth, 2 parts of a space probe weigh 11,000 newtons and 3,400 newtons. These parts are separated by a center-to-center distance of 12 meters and may be treated as uniform spherical objects. Find the magnitude of the gravitational force that each part exerts on the outer in space, far from any other objects. Now, it's important to see how the radius is considering center to center, so we do not need to subtract or add anything. However, because the 2 parts that you're giving are given in weight and not in mass, we need to turn those 2 parts into mass. So we know that the formula for weight is equal to mass times gravity. You have the weight, and you have that g is 9.81. Now, g is 9.81 in this problem because we're on Earth, and the acceleration due to gravity on Earth will always be 9.81 pointing downwards. So using this and using a formula, we can find both of the masses, and you see that mass 1 is equal to 1122, and mass 2 is equal to 346.9 kilograms. Now we can plug it into the formula, which states that the force of gravity is equal to gravitational constant times mass 1 times mass 2 divided by radius squared. Now this is just easy plugging in, and you see that your gravitational force will be equal to 1.8001 times 10 to the negative 7th newtons. Let's look at one last problem. A bowling ball and a billiard ball may each be treated as uniform spheres. What is the magnitude of the maximum gravitational force that each can exert on the other? Now, the bowling ball and this billiard ball are both spheres, so we know that we can use the equations that have been previously taught. Now, we can write out all our variables for both of the balls. However, it's important to note that the radius they're giving you is only for the ball. In order to find the radius between them, we need to add both of them. So it's like this. When you plug it in the formula, it will look like that. And as you can see, you need to add both radiuses because it's not considering the whole distance. So when you plug in values for G, M, and R, you see that the gravitational force will be 9.6 times 10 to the negative 9th newtons.